Next level, this is all about line integrals, right? How to calculate line integral, we have learned two different tools. What we're about to enter is surface integral. Can we have surface integral here? We have two different tools, just like the line integrals. That's the analogy, right? So it begins like this. It's a lot easier than what happened with the Stokes Theorem, so I think it's easier to introduce in here. Motivation is that if you have a line integral, and there was a big discussion about path independence, this amazing property, path independence. This gradient vector field has that path independence, right? If phi is just given to you, not knowing is a path independence or not, and then we looked at the gradient vector field that came up with this cross derivative test, or that was apparent in that Green's theorem. So motivated by these two things, we came up with this mixed derivative test for three variable things, and we call it the curl, right? So that was the operator. Another amazing thing is that if you have vector field there, you can enter curl there in abbreviated notation like that, and then these two things are being the same. That's a Stokes theorem, that's a Green's theorem. So they wanted to try the same thing. If I have a vector field given, not knowing that if it is a curl of something or not, we want to test it like using the cross derivative test. The vector field is given here. You don't know if it is a curl of something or not. Can we do the quick test, not really integrating, decide is a curl of something? So that test is about to be given here, and I hope you can discover that. So this is curl of something, right? The situation is that you don't know R, Q, P, Z, and all that. It is just one simplified formula given to you, one simplified formula given to you, and one simplified formula given to you. We are about to do differential operator to each of these three components to detect it actually came from the curl of something. So just like the curl operator, I just put some differential operator to discover, and how do we, what things equal to each other. Curl being 0 is one idea, and think about, you know, differentiate with respect to what you're doing it here, such that something equal to something. If you pay attention to Ry and Rx, right? If this is going to be ever equal to each other, we got to do something about those two things so that they cancel each other or equal to each other. So what do you want to do to this part that has Ry in it, and what do you need to do that part to Rx in it so that they're equal to each other? Yeah, you differentiate this one with respect to x there, right? Then you're going to have Ryx, right? How about this one? With respect to y, then Rxy, and then these two things are equal to each other, right? So why don't we differentiate this one with respect to x, that one with respect to y? Maybe by looking at that, let's pretend that we also agree that, oh, we're going to do that Rz. For example, Qxz there, right? Where's Q there again? Qzx. Happen to agree, so we're lucky. So let's do that. If you do that derivative with respect to x, what do you get? Ryx, right? And how about here? Qzx. How about this part in here? Pzy, correct? Minus Rxy. Is this right? How about this one in here? Qxz minus Pyz, right? If you differentiate the individual part with respect to x, with respect to y, with respect to z, this is what we get. What is the apparent relationship we have over here is that Qzx, they're opposite sign, right? And Ryx, Rxy, they're opposite sign, it's a mixed derivative. What else? Pzy and Pyz, right? They're all in opposite sign. What do you want to do about this three quantity so that we capture 0? Just like a curl. We add them together and you get what? 0 as a scalar, right? Not as a vector. Curl was a vector. You started with a vector field f, curl it, you get a vector field. But this time, you started with a vector field phi. We do this derivative and add them together and became a scalar, of course, because we add them together, and that scalar was 0. Yes? No, they give a different name for operator, right? This what should we do to this guy so that it captures something nice like that? That operator was described like this, right? The operator is the same as the curl? No. Is it kind of like dotting That's right. I like that. What he just suggested is that if I write it like an operator like this, think about the curl. We use the cross product, right, to capture the curl. What we just did is kind of we multiply these two. Multiplication means applying the operator there and the dotting with that thing that you started with here. These are the vector. Then it becomes what? 0, right? So that must be the correct description of this operator, right? So that's the correct description. What was the name of this operator there? That upside down delta times this phi. That must be 0. That's it, right? Amazing that some of us capture the dot product. The name of this thing is divergence. So that's the descriptive notation, and we call that one, just like a curl was a cross product, the same notation. We call it divergence of phi is this one. I'm going to call that one A component with respect to x, second component with respect to y, third component with respect to z. That's what we just did over there, right? Yeah. If that's 0, it seems like capturing is coming from curl of something. If it is curl of something, that must be 0. So that seems like an operator we should consider. If this phenomena still holds when like the line integral. All right? Yes. Always first component with respect to x, second component with respect to y, third component with respect to z, and remember this is a scalar, not a vector field anymore. Yes. So I think I summarize it so that you can see it a little bit cleaner here. So from that observation, we learned that if you have PQR, it is not the other PQR. It is just components of given vector field. We don't know if it's a curl of something else or not. We consider this operator, right? Instead of ABC, I just wrote it like this. So we use this notation, divergence of phi, scalar, or descriptive like this. It's like a dot product of gradient operator with the vector field. Okay? So what's the theorem immediately we have here? Can somebody come up with a theorem? What we just saw that is that, all right, if you actually look at a vector field that is a curl of something, then if you do the divergence, which is the calculation we just did earlier over there, that should be 0, right? So that's obvious. Curl of something that is already in that shape, curl of phi. If you do this divergence, it becomes 0. Remember the analogous theorem in here? Curl of what was 0? What is inside here? Vector field, if its curl is 0, it must be gradient. So it must be gradient in there. So if you started with a scalar function, gradient and curl dies. This is the vector field, curl it, and with a divergence, dies. Becomes 0. That's the phenomenon. The phenomenon continues to 4 dimension and even the arbitrary larger dimensions. This became the main subject of 18th century geometry. Next thing is that's nice. That's the nice test. How do we know given thing is I think it's a theorem. I stated there and before stated it later that if I don't know if it is this divergence in here, this phi is a vector field of curl or not. If you do the divergence became 0, the theorem is that yes, it is the curl of something, just like the line integral. And curl of 0 means a gradient of something, right? The divergence 0 means is a curl of some vector field. But all this thing is captured in this next theorem. This is the ultimate generalization of Stokes theorem. So the goal is to understand this theorem today. All right, this is a surface integral, right? And what's different is about closed-oriented surface. So is this circle with this boundary here, is this closed-oriented surface? It's not closed-oriented. This open is the edge is there's edge of that surface. But if you take the perfect sphere here, there's no edges here. If you go around, you don't see any of the edges, right? So that's a closed surface. Close up. This one, you see edges of that, right? That's a closed. If I create a little hole underneath it here, so it is those hole, that's the boundary. It's not closed surface, right? But if it is perfectly closed surface, it encloses the solid. Just like a curve in the two-dimensional surface encloses a region in the Green's theorem, right? If you have closed surface in three-dimensional space, it determines inside region and outside region. So it defines a solid. So if it is a sphere, W is a solid ball. Okay? So if you do the surface integral over this closed surface, then you go one higher integral, just like we went from line integral to the Green's theorem, putting things inside the integral by differentiating, right? That's how we prove that Green's theorem. And Stokes theorem as well, which we didn't prove, but that's the idea. Take the formula, differentiate and put it inside the integral. That simple operation is difficult to understand in geometrically physically, but that's what is going on here. If you take that inside, and it captures by this divergence. How do you go from one integral to the two integral? What happened to the vector field in there? What was the operator to go from line integral to the curl is the operator, that's right. Curl, that was a phenomena, right? If it is a closed curve and you can go inside the curl like that. Now we are in the surface integral with a closed surface with some vector field in there, right? Phi. Then you can go inside the triple integral by the solid closed by that. By what operator? Divergence operator. That's the phenomenon captured in here. Alright?
Now, is that only for spherical shapes?
No, anything, any wobbly soap bubble in there, and then that's the surface and the solid inside there. But it has to be closed. Yeah. For example, cube. How about the cube? That's the main application of divergence. This is a boundary, and that's a surface. How many surfaces do you see? Pieces of surfaces. 6 surfaces of a cube, right? So integrating this one involves how many integrals? Surface integrals? 6 different surface integrals. You have to parameterize that. You have to parameterize that. You have to parameterize that. You have to parameterize that, right? Terrible. But if you go over here in divergence, triple integral over rectangular box, piece of cake. That's the easiest triple integral you could ever imagine, right? Triple integral over rectangular box, 0, 1, 0, 1, right? That's going to be really just easiest triple integral, 0, 1, 0, 0, quick calculation. So that's the power of this theorem. Surface integral going over all the like the different pieces, like parallelepiped, right? That would be horrible calculation. But if you go over here in divergence, one quick, Jacobian and a thought, it's quick calculation because the parameterization of the solid of this one is so easy. The parameterization of a surfaces that bounds the solid is terrible. So it's horrible calculation here. It's simple calculation there. That's the mathematical side of what it means. The physical side also, this one captures number of particle it is passing through. And here and there. If it is fluid density particle, the answer is supposed to be what? Going through in there. Net total should be 0. This thing, just to clarify the meaning of a boundary of these three things, because it could be confusing. If you have a line, a curve like that, these two are called boundaries, right? The second line is a closed surface. What is a closed surface here? It's like cube there. That's a closed surface, right? There's no edges. You might look at this as edges, right? But it's not like with open edges. It's more, opening is a better word. Opening is a better word than edges. But you don't see any opening around this cube, right? It's all closed up. That's an example of closed surface. And what is the boundary? Is this surface there? Is this surface there? The 6th surface. And boundary of a solid is the solid is there. That whole thing. Oh, I think non-closed surface, I explained incorrectly. Non-closed surface, it would be just a plate over there. This non-closed surface, and these lines are the boundaries of this non-closed surface. If there's a solid like this, a cube, the boundary of a solid would be all the 6 surfaces together. That's the boundary. So 3 different boundaries is introduced throughout this whole vector analysis section. These 2 points are called boundary. These edges are called the boundary here. And this all surface closed together is called the boundary. Right? This continues to 4-dimensional and even higher dimensional. And the figuring out how these boundaries are put together is important mathematical task, and they succeeded greatly to do that. Mathematics. Alright, so let me just state this theorem here. Already introduced there. If you have a vector field and thinking about whether that vector field is curl of something or not, if you try to actually integrate, you will quickly realize that this is not some integral I can answer quickly. All the technique you might have so far is not going to work. It's a hard calculation. But they're saying the calculation of divergence is easy, right? Just integrate with respect to x and y and z and add them together. If it's 0, they're guaranteeing that it is a curl of something. So that's nice information. Like a curl equals 0, and you know it's a gradient vector field. So I don't think I have much time to maybe I'll show you the big picture and see if I have time for that or not. So let me save it quickly. So at the end of all sections, this is what you're going to get. Before it was computing a line integral, right? Now I'm comparing that with computing the surface integral. So if it is a surface independence, you have Stokes Theorem, right? Stokes Theorem says if you have surface integral like this, you can go back to the line integral. If you can compute this curl of phi, curl of psi, and I just said that this is actually a lot harder than computing the gradient, the potential function, the gradient. So this is not even introduced in undergraduate textbook. No example of this kind. But it is an extension of same idea that I showed you. If you have to calculate like that, I'm going to actually calculate this psi, curl of something, and calculate this line integral. If the parameterization of the C is convenient one, right? But this one is usually introduced in the book. If it is not surface independent, how do you know given vector field is not surface independent? How do you know that? Right, divergence is non-zero, you know it quickly, right? So if it is non-zero, it's worth entering in here. And this is going to be non-zero. So rather than calculating the surface integral with very awkward, complicated parameterization of closed surface all around, you enter triple integral where the parameterization of a solid is really convenient, then you win over here. Right? If none of this thing works, then you have to just go and parameterize this surface and really honestly calculate with this RS cross RT, all that, which is lengthy calculation. That's the third option in there. Alright? So basically this whole section of the vector analysis is about how we are calculating line integral 2 different ways, right? Going back or going higher, one more integral, or going down level of integral, and surface integral, going back down to one integral lower level and pushing another higher integral level. Sometimes this thing benefits the other and things like that than the other. So that's the big picture of this one. And on top of it, mathematicians love to talk about this surface independence. When is a surface independent? When is not surface independent? If you think about it, the book does not have enough proof about if it's a path independence. Why is a gradient vector? I didn't prove it. The book does not probably give you the sufficient proof in that, but it is true. So that's a discussion that is usually not covered in undergraduate courses, but it is, covered in second course of advanced calculus or something like that. But hope that big picture makes sense to you. It's all about, to us right now, about computing line integral in 2 different ways, surface integral in 2 different ways, plus there's a direct calculation. Okay? So I apologize, we didn't have enough time to actually go into this calculation of divergence and actually feel that, how it's used and things like that. But I read those example in the book, which example 3, like that is direct calculation. It's just putting to divergence, and divergence is a lot easier to than calculate the curl, and integral is very simple. And I definitely feel like you can read this example 3 and 4 and 5, thoroughly understand what's going on in the solution, because it's a lot easier than the surface integral. So I encourage you to do that, right? Go ahead and read that. However, it begins with the awkward part. Just go to this example 3 and that part will make sense. Okay, there wasn't any in-class exercise, was it? Right, so I'm not collecting anything, but you have a lot of work to do today until Friday. So I'll post the mock test, and thank you for your great attention. I have this thing prepared I forgot to show you. Go ahead and learn more linear algebra and continue into differential geometry, then you will understand the general relativity. And that's an amazing epitome of this beautiful marriage of mathematics and physics. All right?